get started. So, quick announcements. I put a new extra credit assignment up. There's a speaker coming in about a week, I think a week from this Friday. Dan Jeske, who's from UC Riverside, is actually giving what's supposed to be a very accessible talk about statisticians' debate over whether p-values should be replaced. And so, if you're interested, or maybe even if you're not, there is I added a bonus homework that's I call it homework. It's like a bonus lecture, and there are 3 questions. Well, one where I say, what does he list are the main problems? 2, I ask, what do you think is one of the sort of interesting solutions that he posed? And then the 3rd question asks you to go and find this article online and or find this journal issue online and list a couple titles from the content. So it should be pretty low key, but at least for the first 2 questions, and then that will be so that's like 5 points. So that would be like replace like 5 lecture attendance misses or something like that. So that's online. The announcement, I think, is automated to go out right after class, but you might already see it on the calendar as well as in the assignments. It's totally optional, but if you're interested, there is that lecture bonus online. So, and the announcement is this flyer is also on Canvas. Otherwise, so this is the last week for labs. So it's the last lab this week. It's sequences batching and a little bit of SimOpt. And so this is also a lab with significant bonus. So if you want to make up for some other things in the past, then you can feel free to make use of these 20 extra points. Otherwise, the first part kind of fills out all of the normal points. So the second part is just kind of a bonus. But I would recommend at least looking at the process analyzer and OptQuest, because if you get at least a little familiar with process analyzer, it will make homework J2 a little easier. And it may actually make your final project easier because it sort of automates the running of your experiments. You don't have to manually change parameters, run things, change parameters, run things. It'll sort of do all that for you. So even if you're not interested in the bonus, at least take a look at these things, because I think the process analyzer intro will be useful. I also think that some of you might find batching and signaling and holding to be very helpful programmatic elements. So let's say you're modeling an intersection, a signal intersection, or an intersection with a traffic signal. That is a great place for using signaling and holding. So you want to hold one direction until the next direction is ready, and vice versa. That also it plays naturally into batching. So you want to hold up a process until a certain size batch is available. So if you imagine your process waiting for a particular condition before it can go on, then you probably could very easily implement that with signaling and holding, and I recommend at least taking a look at that even if you don't want to go through and do that part of the lab. So that's the last lab, and then after that, the 2 other weeks before the presentation, we've just got marked for open labs. And so if you need extra help, sort of extra office hours time, then that time the TAs will be available, and if you make appointments, I can also be available. But there's no formal activity, there's nothing graded, it's just open time to give you time to make sure that you can work on doing the programming or the analysis. Then the final project, so everybody should have feedback on their input modeling reports. I also gave kind of generic feedback that was accumulated from all of those, and that's in a Canvas announcement. The next deliverable is your group presentation, which is the last week of class. And so gradually these announcements will become more about that. But basically, if you're already thinking about how that's going to be structured, everybody's going to have 13 or 14 minutes. So plan for 10 minutes of presentation and 3 minutes of Q&A. And so it's always good to go short and not long, because we'll have to cut people off to make sure that everybody has enough time. And then, depending on people's availability, then I usually not only have me and the TAs evaluate you, but try to bring in other faculty or other grad students who might be available at that time. And then there's a form online that's kind of a rubric that they kind of check and say. And so you're kind of presenting to a mixed audience, and so you want to make sure that your presentation kind of well motivates what you did and why you did it and what your results were. And then the Saturday before finals week, that's when your report will be due, and the format for that's on Canvas. It's basically a 4-page report but there's room for an appendix if you need to spill over and put extra details. But it should be hopefully a relatively short or small demand, and I think these 4 pages will go very quickly when you start including all the things you need to include. So, any questions about labs and final project moving forward? So the last sort of new ICA is ICA-L, but I've also made the final exam review ICA available. So, and that's the one you can take as many times as you want, and it just kind of randomly samples from all the ICAs before it. And so I've also put sample midterm or sample final exams online. So keep in mind that because I'm doing the retake schedule for the first time this semester, your final exam will be more midterm length so that I can fit the pre-take during the normal class period. And that also means that then during the final exam period, we won't go the full final exam period. We'll go just kind of a lecture period during finals week. Question?
So that means that the pre-take and the retake won't be cumulative. It's just like the second half.
No, will be. So I would say it will be cumulative, but there'll be more of a bias on the second half, and there's more sort of an integration. So yeah, we might talk about the inverse transform method, but we'll kind of fold it in with a question that involves some of the more statistical topics that we've come up with, since then. So I'll try to find a way to blend some of the first semester stuff in with the second semester, or the pre-midterm with the post-midterm stuff. So the intent is to still make it cumulative, but of course the bias will be more towards the end. But it's my kind of feeling that a lot of what we've been doing kind of builds upon what we did. So we did the KS test and the chi-square test beforehand. I still think it's really important that you know how to do a hand simulation, all of those sorts of things. And so yeah, don't expect it to be like all about confidence intervals or something like that. And then homework J2, that's been online. This is an arena-based homework. This is the final homework assignment. And you can do all of it by hand, but if you know how to use the process analyzer or OptQuest, it may make it go by a little more quickly. So again, I would recommend taking a look at that in Lab 10, at least the videos that are posted for that. And because we kind of use this to capture an A-bit metric, there won't be like a solution set, but this is largely sort of meant to be kind of a mini lab exercise anyway, where you take some of the stuff you've learned in lecture and apply it to a lab assignment. You'll modify a previous inventory management model that you've worked with. So it's much more kind of arena-like than a lot of the other homeworks anyway. Yeah.
The retake is the Thursday before finals?
That's right. So basically the schedule that last week of finals week is Tuesday we'll do a midterm review. Then Wednesday is lab, and that's when everybody presents. And then Thursday is the pre-take. And then Tuesday of finals week, I'm pretty sure that's the day that we've been assigned, is when then we've got the other final. So if you just don't want to deal with the final the last week of classes, then you don't have to come to the pre-take, and you just take it during finals week. If you'd, or the other way around, if you just want to get everything done and not come to finals week, that's fine too. Or if you want to take both, that's totally fine. So there's no fault either way. We'll just take the highest of the two scores, just like the midterm. Any other questions about that? Yeah.
Do you think like grading will be cut up by then? Because I know a couple of labs were still not. Like, we'll be able to know by that. Like,
yeah, I mean, so part of the reason why we give all this extra time is so that I can just have the TAs catch up. It takes them a while, just because some of these reports kind of get longer, and there's a lot of variance across these reports. And I try to apply as much pressure as I can, but this is sort of meant to be. Hopefully caught up in hopefully the next 2 weeks we'll actually see a lot of improvement because there's a lot less that they have to do, for me at least. So, any other questions? All right, so let's. So where we've been is we've now introduced interval estimates, and now that we've introduced interval estimates, then from this point on in this course and in the rest of your life, you should never give a point estimate ever again. Point estimates are bad. They don't communicate your uncertainty in your estimate. So in some ways they're kind of disingenuous. The only time that so point estimates make sense if you've got so much data that effectively your confidence intervals would be minute. if you did calculate them. But in most of your cases, if you've only got a handful of replications, then you're always going to have uncertainty on these estimates, and so you should always use interval estimates. If you read papers, then people will always have an interval estimate. They might have their point estimate next to it, but the interval estimate is always there to communicate their uncertainty in the interval. And so if your data are IID, so that's independent and identically distributed, and you have at least 5 of them, then regardless of how they're distributed, it's usually safe to use a standard error of the mean as a half-width. So there's not a lot of utility to this, so it's not like you can apply a particular statistical test by looking at this, but at least communicates if you were to take data again, where you think the mean might be with respect to the center of this confidence interval here. And so if you say, well, what do I have less than that? Well, if you have less than that, then maybe you should gather more data. If you can't gather more data, if you only have 4 data points, what are you doing summarizing with a point estimate anyway? Just show me the 4 data points. Because 4 data points, you can't even get a box and whiskers off of that. So it's crazy to take 4 data points, turn them into a mean, and then try to fake an interval around them when your interval has more data than the 4 data points to begin with. And so if you've got 4 or less, just show me the data. If you've got 5 or more and you don't know about the distribution, then an SEM. But if they're normally distributed, then that's kind of the gold standard where show me a confidence interval. And we'll see in a second here, the confidence intervals actually can be useful and functional. And then if they're IID but they're not normally distributed, then very often you can transform them, and I've kind of hinted at this. So you can take data that are shaped in funny shapes, and you can say, take a logarithm of that data, and then look at the distribution of the log of that data. And then that might be normally distributed, in which case you can do a confidence interval in the transform space, and that also can be useful. And so there usually are methods of getting back to something that acts like a confidence interval. In the worst case scenario, then if your data are not independent and identically distributed, especially with the not independence, then you might be in what's a phenomenon we refer to as pseudo replication, where you thought you've taken a lot of data, which gives you a whole lot of information, but really you're just getting multiple copies or multiple looks at the same phenomenon, and it's really just one sample. So like if you were to sort of study if you were to take a honeybee colony or something like that, and you said, oh, there's thousands of bees here, so I'm going to measure some physiological measurement of every bee. You'd say I have thousands of data points, but it turns out your one colony was just weird. It just happened to be sort of amped up on a particular hormone or something like that. And so if you went to another colony, you might get totally different measurements. And so when biologists talk about sampling from these like populations, like honeybee colonies, their unit of replication is the colony, not the individual, because the individuals are effectively correlated with each other. Similarly, it would be crazy for a scientific study to only do work on just people of one family. They need to make sure they balance out across families, across locations, and so on. So independence is really important, and if you don't have independence, you probably don't have a study. You probably just have a measurement from effectively a single replication. It might look like a lot of data, but it might only be 1 or 2 replications. Question?
Yeah, how would you be able to detect pseudo replication in your data?
It's really all about the design. So if you look at the design of the experiment, you have to ask yourself, did I hold up my end of the deal in making sure that I've got independent samples? And we're going to talk about that for how that is in simulation. In simulation, you basically make sure that I have different random number seeds going into every replication. And then I can be pretty confident the data out of a replication is going to be different than data out of it from another replication. But in other studies, it can be a little harder to figure that out. And there may not be a signature of it in the data, but the inference you make based on the data will be flawed if your design did not make these things independent. These designs are a little easier to make independent in simulation, but we're going to talk about today when you're taking data out of steady state simulations, then you do run into this problem and we have to deal with it. Yeah.
Kind of a question from way back, but so how would you, can you give an example specifically of what identically distributed versus not identically distributed data would look like?
Sure. So, I mean, the idea would be is that let's say if in the case of simulation, if I had a simulation model and I took a bunch of data on wait times or whatever, and then I just decided to switch to a slightly different simulation model, like, oh, I noticed I wanted to fix a bug in my code. And so I fixed that bug in my code, and then I continued to take the data. If I pooled those two data sets together, then that would probably be a bad thing because my first samples might have a different distribution than my second samples. So in the case of simulation, we normally get the identically distributed for free because we usually are pooling data only from within a certain simulation model, and we're only going to get a different distribution if we switch to a different model. So the independence ends up being more important for us than the identity. But in general studies, you just have to be careful that, I took a data set from men or women, or I took a data set from dogs or cats or something like that. And if you can't pool those data together and take an average across all of them because the variance structure is going to be really weird. I need to split out the variances first and say, okay, these are all my dog data, these are all my cat data. This is my dog average, my dog standard deviation. This is my cat average, my cat standard deviation. It would be wrong to pool those together and say, this is my animal average and my animal standard deviation. All right. So let's focus on those confidence intervals. I want you guys to be building up your intuition on confidence intervals because when we go to relative performance estimations next lecture, then we'll see a lot of these. And so the idea here is that I look at this confidence interval, which I've sort of summarized here as in minus h and plus h, where h has got this funny formula. And so the question is, why is this particular interval useful? How could it possibly be useful? What does it mean? And so we can do a little experiment. We're experimentalists, and so we go into Excel, and it's a little hard to see, but there's just a bunch of random numbers here. And what I've done is in one of these cells up here, I've put a formula like this one. This is inverse transform sampling applied to a normal random variable in Excel. So if you want to ever draw a normal random variance in Excel, Excel has given you a norm_inv function, which is their approximation of the inverse CDF of a normal. And so you can draw a random number between 0 and 1, and you can give the norm_inv a mean and a standard deviation, and then that will end up drawing out replicates from a normal distribution. In this case, a normal with mean 5 and standard deviation 0.1. And so if I fill that in this column here, and then I filled right, then I end up getting a bunch of samples, so whatever, 18 samples I think here from a normal distribution. And so my question is, how does a confidence interval relate to these samples? And so what I've done over here, you can't read the numbers here, but the basic idea is in this column I took the average of all of these. And in this third column I took the standard deviation of all of these. And with the average and standard deviation, I can calculate the half width. Unfortunately, Excel has already a confidence.t where it'll calculate the half width for you. It does all the work for you. You give it a significance level, 0.05, you give it the standard deviation, you give it the number of data points, and it'll calculate the half width for you. So down this column, I've got averages, and down this column, I've got half widths. And then I can then ask, I know the real mean, and actually I think I've got this sort of highlighted, maybe I should have jumped ahead here. So that was the normal thing here. I've just calculated my half widths, my 95% confidence interval half widths. So the next step is then, how often do those half widths contain the real mean? So I can write a little formula where I know the real mean is 5, and I can basically do a little and here, and I've kind of added a little pseudocode in with the Excel, where I'm basically saying this column comes up true if the real mean 5 shows up in the calculated half width. And so I've got all of those, and I can just fill this thing down, and then I can plot all those half widths. And I can count how many of them actually contain the real mean. And so I've plotted the real mean as this line across here, and I'll just go this way. And so this is the real mean here. And I've highlighted it so like this first half width, this blue one here, it contains the real mean. But all of these other kind of fuchsia colored ones are the only half widths in this set of, I just happen to fill down 187 rows. But out of these 187 rows, only 6 of them did not contain the mean. And that 6 out of 187, that is very close to, and as expected, the false positive rate, the 0.05. So that's what we're getting at when we talk about a half-width, is that a half-width is such that what's the probability that it will contain the real mean if the hypothesis is true. And under the assumption that the hypothesis is true, 95% of the time, the half-widths you calculate will include the real mean. You won't know what the real mean is, but you know it'll be in there. So if you exclude anything outside the half-width, outside the confidence interval, you'll only be wrong 5% of the time. So that's kind of what we're showing graphically here. So like if I'll sort of get maybe a little cleaner resolution here. So if I have a low alpha and calculate these, so this is like, I think I've used an alpha of 0.001. So these are confidence intervals that are 99.9% confidence intervals. So I'm really confident in these confidence intervals. Well, what does it mean to be really confident? That means that 99.9% of the time, when the hypothesis is true, the mean, the true mean, will be in these intervals. The only way you can make that happen is to have gigantic intervals. So all a high confidence interval is a confidence interval that is huge enough that you can pretty much guarantee the real mean will be inside there. So I made my alpha low, it made my confidence intervals high, and notice that all of the confidence intervals contain the real mean. Now if I go to a more conventional alpha, like an alpha of 0.05, then now I see, so I basically did 3 different experiments. And so these experiments, so in here, this is just 100, 100, and 100. I just ran this 100 confidence interval experiment 3 times. I did the same thing here, 100 confidence intervals at 0.05, another 100, another 100. And roughly 5%, so roughly 5 of these I've highlighted, do not contain the mean. So 95 of my 100 confidence intervals contain the mean, and that is because they are 95% confidence intervals. That is the interpretation of what a confidence interval is. And notice they got a little narrower. So as they got narrower, I got more discrimination ability, but I started making more false positives. I can go a little bit farther and I can say, well, what if I have a really high false positive rate? Well, really high false positive rate, in this case, I chose a 0.6, so 60% false positive rate. So these are 40% confidence intervals. And notice the confidence intervals are tiny. So every confidence interval sort of gives me the impression that I know very closely where that mean is. But it turns out that a lot of them are wrong. 60% of them don't even contain the mean. So that's what happens as you go from a low alpha to a high alpha. Your confidence intervals get smaller, and you stop capturing as many of the means. So the number in front of the confidence interval, that is the fraction of confidence intervals that will capture the mean if the hypothesis is true, if that mean is the real mean. So there are questions about that interpretation. So this is normally the confidence interval that we use for the 95% confidence interval. It is a measure of our certainty of where the mean is. It is not a measure of the distribution. For this estimator, where is the mean? If you want really, really high, so here's a question. So what would an 100% confidence interval look like? Talk to your neighbors. 30 seconds, and then I'll call them. So the question was, what would a 100% confidence interval look like? What is a 100% confidence interval? All right, so let's get back in. So what is a 100% confidence interval, and why is it not a useful thing? Lexi. Oh, sorry, I thought you saw your hand up. I'm sorry. The stretch. Anybody else? Yeah. That's right. A 100% confidence interval is the entire real line. So the only way we can be 100% confident that we've got the mean is by covering the whole real line. And that's why even it sounds like if 95% is good, why don't we just take it to 100? Well, if you take it all the way to 100, if you turn it to 11, then what you end up finding is that you get a useless estimate. You're basically saying the only way we can be 100% confident is if we just don't even know where the mean is. So it's anywhere, it's somewhere. We're 100% confident it is somewhere on the real line. So we back off a little bit and we say, all right, how about 95%? So then now we can say, okay, now this is a manageable size. So that's so a 0% confidence interval. Well, that's the one that is just a single point. And so when you're giving somebody a point estimate and you're not giving them a confidence interval, you are implicitly giving them a 0% confidence interval, which is basically you saying, I actually am not confident about this at all, and I am 100% sure this is not the mean, but here's my estimate. So a point estimate is your way of telling someone that you did not listen to them and you're giving them a different answer. So you give them an interval estimate, and that tells you that 95% of the time, my interval will contain your mean. It would be great if I can make this smaller while keeping it at 95%, and we do that by using our statistical power. So if I get more samples, so up here, I've got the same experiment, but now 95% confidence intervals for all three. But up here, I've got 20 samples. Here, I've got 200 samples. Here, I've got 2,000 samples. So in all of these, it's a 95% confidence interval. So you still see roughly 5 of these fuchsia dots. So 5 of these fuchsia intervals in each one of these. But we see that as we get more samples, our confidence interval gets tighter and tighter. We start rejecting more and more and more alternative hypotheses, and we get higher sensitivity. So if you really want someone to have more confidence, or if you want someone to have more sensitivity at the same level of confidence, you increase your number of samples. Or the other side of it is variance. So I've gone the other way around here, where now I've got 95% confidence intervals, the same number of samples. I think I did 30 samples in each one of these. But I did a variance of 0.5, a variance of 1, and a standard deviation of 0.5, a standard deviation of 1, and a standard deviation of 2. And like you can see here, for a 95% confidence interval, as you increase the variance in the data, you end up increasing the size of the confidence interval and reducing the sensitivity. So if you need smaller confidence intervals, the trick is not to change your alpha. It's to change your beta. It's to increase your number of samples or to increase your variance. Decrease your variance. And so what we'll see after this unit is how we can start decreasing our variance by using clever experimental design tricks in the simulation. For now, this unit is all about choosing the number of replications so that you can effectively get this interval down to a manageable size. So, are there questions about this basic interpretation? So where does this come from? Well, if you think about it, this is our T criteria. And so we can say that this criteria here is true with probability 1 minus alpha in the case where mu is the true mean. So if data are drawn from a distribution that have this mean, then we know that sometimes we're going to get estimates of the mean, x bar, that are far from the mean, just by random chance, just bad luck. But most of the time, then we are going to get estimates that are inside the kind of very close to the mean. And so this t statistic will be less than this critical value here that we look up in a table. So we can unpack that a little bit because there's an absolute value, and we can say, all right, well, what if we're in the case where my estimate is greater than the hypothetical mean? And then that allows me to algebraically unpack this inequality and turn it into this inequality. And this inequality is identical to that inequality, but I just moved the critical t value over so that the relationship between x bar and mu is more obvious. So if x bar is greater than the hypothetical value, then we're basically saying that x bar must be between this lower bound and x bar. Now, in the other case where x bar is on the other side of mu, we can do the same unpacking, but we've got a negative we have to deal with, and so it flips things around a little bit. And we see that now, in this case, we know that the true mean is packaged between x bar and this upper bound. So when we combine those two things together, that's how we get our confidence interval. And so a confidence interval really is just a graphical depiction of a t-test. You said, given that if the hypothesis is true, then the probability that the true mean is within the confidence interval is 1 minus alpha. And that's why it's a 1 minus alpha confidence interval. It's the mathematical origins of the confidence interval. So this allows us to then have these very simple heuristics that we can use to evaluate t-tests without actually going through t-tests. If I give you a confidence interval, if the confidence interval does not include some hypothetical mean, then we reject that mean. So somebody says, I think that the average wait time is 5 minutes, and you run your simulations, or maybe you just go out and real data, and then you come back with a confidence interval, and that confidence interval goes from 7 minutes to 15 minutes. You'd say, I'm sorry, at 95% confidence, I'm pretty sure that your 5-minute guess is wrong. It turns out the wait times are at least 7 minutes. So they're somewhere between 7 and 15. I don't know what they are, but I know they're definitely not 5, at least at the 95% confidence level. So that's kind of the simple rule there for evaluating the kind of one sample t-test without actually having to do a t-test. So a 2 sample rule is if I give you 2 confidence intervals of independently drawn data, then if they do not overlap, then the processes that generated these 2 confidence intervals probably don't have the same distribution underneath them. So the idea here is that this is a graphical depiction of a 2-sample t-test. If I have a confidence interval that does not overlap with another confidence interval, I don't need to do a 2-sample t-test. The 2 populations are significantly different. So, and then if somebody gives you a standard error of the mean instead of a confidence interval, and you assume that the data are normally distributed, then you can get confidence intervals out just by doubling the standard error of the mean. And that 2 comes from the fact that the critical t-value happens to be really close to 2, especially as your number of samples goes up. And so with that in mind, like if somebody gave me these data, which is the example I did last time, here they gave me SEM bars, and they might have given me SEM bars because these data are not normally distributed, and they had no business generating confidence intervals, because you can't generate confidence intervals if it's not normally distributed. But sometimes people just prefer putting the SEMs instead. And so if we have some reason to believe that these data are normally distributed, if I double these SEMs, I see that the doubled version, so imagine this being slightly higher and this being slightly lower, they end up overlapping. Because they overlap, I cannot conclude anything without doing a formal 2-sample t-test. But if these were the confidence intervals, I see that they don't overlap. And if these were the confidence intervals, then I would say that this 2-sample t-test, if I were to do one, would come out statistically significant. And this population would be different than this population. So that's a quick graphical way to do these stats. So the other thing that confidence interval gives us is because the only time you ever generate a confidence interval is if it's normally distributed data, then if I know the confidence interval and the number of replications that were used to generate the confidence interval, then I actually have a full input model of that process. Because I know the process is modeled by a normal. And I know that I can back calculate, if I know the number of replications, the standard deviation given the confidence interval. And so knowing the middle of the confidence interval, the mean, and the standard deviation, which I get by looking at the half-width of the confidence interval and the number of samples, then I can model the entire process as a normal with that mean and that standard deviation. And I can get whatever I would want to get out of that. I could get quantiles out of that, I could get a CDF out of that, I could get a PDF out of that, whatever I want. I've modeled the whole thing, and I've communicated that just by telling the reader what my confidence interval was and how much data I gathered. So confidence intervals are input models, but that's why we can't use them unless we know the data are normally distributed. Are there questions about any of that? Where the confidence intervals come from and what we can do with them? And sort of this hint here, and you've already sort of seen this in your labs, is that often, like Arena will give you half widths, 95% half widths, and we might ask you to do arithmetic on those, like convert that into a 90% half width, convert that into a standard deviation, and so that's where these formulas come into play.
Just to clarify real quick, but like how come that you cannot you can only use confidence intervals if your data is normally distributed? If there are like I believe that there are confidence interval formulas for other distributions. So like how's that?
Excellent point. So it's slightly more advanced, but you can generate confidence intervals for other distributions. They're still parametric, so you still have to say, I have to know what that distribution is ahead of time. If somebody doesn't tell you that you're working with a special type of confidence interval, it's usually implied that normality is the underlying distribution that is used to generate the confidence interval. But certainly you can use mathematics and fancy sampling methods to generate confidence intervals for other distributions. But then you have to communicate that this is a 95% confidence interval relative to some other distribution. So definitely you can do that. But in this class, and I think in most kind of like normal, just sitting around the coffee shop chatting, the 95% confidence interval is probably going to be the norm.
So that means like if you want to calculate confidence intervals for other distributions, you have to go into like parametric tests and all of that.
Well, like I showed you kind of the basic background for where we get the confidence interval formula for the normal. You sort of follow this process for whatever you're sort of assuming. So if you assume some other distribution, then you're going to have some criteria that will be true when your hypothesis is true. And you have to say, how do I turn that into a confidence interval? And that process may be almost identical to this. But like for a z-test, for example, you can calculate in Excel, there's confidence.norm. And it will give you a confidence interval for a z-test as opposed to a t-test. So if you have some criteria like this, it's easy to generate that. But your criteria might be like something that's like generated with a simulation, or it might be very difficult to calculate this, in which the only way to really get a confidence interval is actually to do simulations of your hypothesis test and then see how often it goes wrong and how often it goes right, and then kind of bound those things up together. So it can get very complicated in how you generate these confidence intervals. It just is nice and tight and compact for the normality case because of this t statistic. But and so sometimes they're as simple as this, and sometimes they're more complicated. But so yeah, and sometimes it's just nearly impossible to do without a lot of computational power. So if worst comes to worst, use an SEM. But if you can, use a confidence interval. All right. So, and that goes for quantiles as well. So if somebody asks you for a median, so a lot of times people say, oh, I hate the mean. Give me the median. And there's good reasons to do that. The median is a more robust statistic. But you also don't have high confidence where the median actually is. You might have a little bit more of that, but it's nice to then also put an interval around that. And so we talked about that last time briefly, but the idea here is if I'm asking you for the p quantile, so for a median this would be 0.5, but I might ask you for the 85th percentile, this would be 0.85. If I know my number of replicates, and if I have kind of sufficiently large numbers of them, and then when you're doing quantile estimation, you're probably going to have 20 anyway, so you're probably going to meet this. Then you get this thing that's kind of like a half-width, but it's like a half-width in probability space, and you'll use that to pick the rankings of your data. So the idea is you sort all of your data, and you need to say, I'm going to grab one of these data points and call it the median, or call it the p percentile, and then I'm going to grab data points around it, and then I'll use that to say that's my interval around that. And so the idea here is that your confidence interval is going to be a data point at the rank that is the number of data points times this PL, where PL is the probability defined by this. And then the other one is I type the number of samples times the PU, which is just a probability which is calculated by this formula. And so this gives me these two data points, one that'll be slightly to the left of the my point estimate of the quantile, one to be slightly to the right of the point estimate of the quantile, and then this interval will be my 95% confidence interval for the quantile. So if it's easier to say, median is a good conceptual model of thinking how this works, as opposed to saying like the 95% confidence interval of the 85th percentile. Like that's just like a lot of percents in one sort of sentence. But it works as well for median. So if you wanted the 95th percentile interval estimate of the median, then you would get something like this, and you would have roughly the midpoint of your data in the middle of this thing, and then you'd have a few steps to the left and a few steps to the right, and that would be your confidence interval. And exactly how many steps to the left and the right is defined by this formula here, which basically makes some assumptions about binomial distributions and some other things that we won't go into the derivation for. But it just goes to show, like we we're just saying, you can generate confidence intervals for other types of assumptions. And you should always look for a confidence interval if it's available. Questions about this? I did an example of this on the last one, if you need to see this sort of written out with numbers, how to do an interval estimate for quantiles. All right, and then the other thing that we introduced last time was then, and then applying our confidence intervals to this, which you did in Lab 9 as well, is these terminating systems with transient simulations. And so we said that one of the types of systems that we simulate is a system where we care about where the system starts, and we care about where it ends, and we accumulate per replication data from the entire simulation. So we really do care about this transient. Since we care about the transient, it's something we simulate and want it to be accurate, then we refer to these as transient simulations. So we don't worry about this initialization bias because we've got all of the data here is good data. And so now our question is, how many of these do we run? If this is one replication, do I run a second, do I run 5, do I run 50? And so there are two methods for doing that. You could go back to homework G3 where we learned about power analysis. So in that case, I could say, I'm going to run a t-test. I want you to detect this effect size, and I want you to have 80% statistical power. And if I give you those pieces of information, you can come back to me and say, well, for this standard deviation, you need to gather 20 samples. And so I can run a pilot study to estimate my standard deviation, plug that into the power analysis, and then come back. And then power analysis will use operating curves, or realistically, nowadays, you just use software to do it. And it'll say you need to run 20 simulations. And if you already ran 5, maybe you just run 15 more, and you can pull all that data together. And this also could apply to any design of experiments, not just simulation studies. What we're going to talk about today, or what we actually technically already talked about in last lecture, is an alternative approach, which you did in Lab 9, where it's not a formal power analysis, but it's where we say, I don't necessarily know exactly how much statistical power I want, but I want my confidence interval to be a certain size. So I want my half-width to be a certain fraction of the mean. And so in those cases, I specify my desired half-width. I then run a pilot study, just like in this one, to estimate variance. From there, use that estimated variance to guess how many more samples I need to squeeze that confidence interval down to a smaller size. And so the formula we use for that, and which you should have used if you did Lab 9, is something that looks like this. And so we basically have to first assume that our replications are independent, which usually in a simulation, at least in a transient simulation, we get for free because we use different seeds for every replication. And Arena will give you a different seed for every replication, so long as when you go to run setup, you say I want to run 50 replications. If you start Arena 50 times, every time you run it, it uses the same seed. So those 50 data are not independent. But if you start Arena once, tell it you're going to run 50 replications, then hit run, then all of those will be independent. And then normality often holds for across replication data because usually you're summing up. And so you might be accumulating over this whole time, and sums tend to be normally distributed. But although I'm not going to push for it, I'm not going to push you to formally do it in this class. As you come out of this class, before you do any of this stuff, then you should at least try to do a QQ test, if not a Shapiro-Wilk. And in Lab 9, I think we at least had you look at the distribution of values to see if they kind of look hump-shaped. And that was kind of the poor man's version of a QQ test. Does it pass the eyeball test? Once you have that, then if you run your pilot study to get your basic variance here, then you can calculate, so using the half-width formula, we do a little algebra, and I can plug in my desired half-width my estimated variance and the t-statistic for however many replications that I want. Now, it's a little weird to say, well, how do I know what t-statistic to use? Well, if I make my replications really large, the t-statistic becomes the z-statistic. And so this ends up being the convenient formula you use. You take whatever the estimated variance was from your pilot study, you multiply it by the critical value corresponding to your alpha over 2 from the z, from the standard norm, and then you divide that by your half-width. And that thing squared gives you a lower bound for the number of replications you'll probably need. So if you already ran R naught, you can just run whatever the balance is. And then those will be more independent observations that should hopefully bring your confidence interval down. Doesn't always work perfectly because you might have got unlucky in your pilot study and it might have looked like less variance than it actually is. But it'll at least get you closer. And then from that, you then can figure out, oh, I might need to run 5 more. So does that make sense? Any questions about that? What is the downside of running more replications, which I'm hoping you appreciated when we had you run a lot of replications for some of these, especially if you didn't read the thing about batch runs. So what's bad about running? Why not just say, always run 1,000 replications? Kind of an easy one. So any thoughts? Take 30 seconds and talk to your neighbor. What's bad about just saying, always run a lot of replications? Why are we always looking for the fewest number of replications to run? I can actually think of 2 reasons, but go ahead and chat with your neighbor. All right, let's bring it back in. So what's bad about running extra replications? Why do we want to reduce the number of replications we run? What happened in the labs when you were asked to run, like, I don't know, 50 replications of that manufacturing system model? Was it instant? It was slow, right? So, and if you didn't turn on the batch runs, even if you fast forwarded, each replication seemed to take forever. So the computational burden, the budget you have, is such that even with simulation, where it seems like, well, we're simulating these things, how bad could it be? It's not a real system, but it still runs a long amount of time. And so we always want to get as few of these as possible because we probably don't have all the time in the world, and we might need a lot of replications. But if we, choosing an arbitrary high number like 1,000, it might take a week to run 1,000 replications of some of these simulation models once they get really complicated. So I've certainly ran simulation studies that have taken a month, and so if I made a bug or something like that, I would have to run pilot studies to make sure to verify, and then run pilot studies to validate. And then once those, I unleash them, and then hopefully when I come back, a month later, then I've got data that I can trust. So these things do happen. It just kind of depends on what experiment you're running. And hopefully you've got those experiments were not very narrowly defined. If you have a narrowly defined experiment, you probably don't need to run it for that long because you can focus on things, but those were very exploratory. So I had a lot of treatments and a lot of replications. Yeah.
So how would you determine your minimum number without sacrificing confidence?
Well, you set the confidence. You say, when somebody sets the half-width, they're saying, I want my 95% confidence interval to be this big. And so then you have to run a pilot study and hope that your variance estimate from your pilot study, which only has 5 replications, is a good one. And then from there, hopefully then that will determine that, okay, you need to run 100. So then 100 only takes a week to run. So then I run this 100 for a week. And then after that, I can check my variance again, and if I need to run a few more, then that's fine. But a critical thing is that, and this seems a little mysterious, it's okay to check your variance ahead of time, but you never want to actually look at the interval until the end of the experiment. Because you don't want to tempt yourself into running more simulations until something magical and coincidental happens. So we run these pilot studies not to get an idea of where the confidence interval is, but just how wide it is. And then once we kind of decide that we've run enough for it to be sufficiently narrow, then we look at where it actually is and then make an inference about our mean versus the confidence interval. So that's the key sort of question for these terminating simulations. And so, so let's do a quick attendance question here. Now we've got confidence intervals in mind. And so all I'm asking here is for a letter to put down on your question 1 on the attendance exercise. Was that if I give you 5 samples of normally distributed data, then choose the option below that is the biggest confidence interval, like the one that is the widest confidence interval. It takes up the largest chunk of the real line. And basically these go in gradations from 1% to 99%, or I give you a escape hatch where I say, well, it might depend on the data set. Sometimes the 5 samples are going to be here, sometimes it's going to be here. So can you make a general claim that one of these is always larger than the other? And if not, then that's your answer. So which one is bigger? So that's the attendance question. So you guys kind of mull over it. Does anybody have a guess as to what they think the right answer to this is? How many, actually I'll do a little vote. How many people think the right answer is A? How about B? How about C? I saw like 1B, 1C. How about D? How about E? All right, looks like most people went for E. How about F? All right, and then there's a couple of Fs. And so the distribution were like 2 or 3 Fs, mostly E, 1C, and 1B. My answer would be E, because in order to gain confidence for the same sample, same variance, same everything, if you want to gain confidence that you've captured the mean, all you can do is make the interval bigger. So remember, this number is how likely did you capture the mean if you assume that the hypothesis is true. And so the only way to do that is to make the interval bigger. All right, so now we focus on steady state simulations, which are what we focus on for these non-terminating systems. So a non-terminating system is a system where I forget about the history of the system and I really only focus on what it's doing as it's normally operating. In order to get a simulation in that mode, I have to start the sim, so the simulation has some transients, but those transients are meaningless. And so I don't want to include them in my data set, or else I will bias my estimate of the normal operating behavior, of the steady state behavior. So the question is, how do we get rid of this initialization bias in an efficient way? And so in Lab 9, we talked about how to set a warm-up period. So how much to truncate. Here, we're also going to introduce, well, do we need to increase replications, or can we do longer execution times? And so for these particular types of simulations, for the transient simulations, the big question was how many replications to run. But for these, they introduce an interesting wrinkle where we can actually trade replications for length of simulation. And so sometimes we can actually run the simulation for longer, run fewer replications, and actually get the simulation done quicker, and actually have less bias and less variance, so tighter confidence intervals. So we'll see how that works here in a second. So basically now we're estimating these limiting performance characteristics. So from the real system, if you had a tally of data from the real system, you take the limit of the averages as n goes to infinity, and that gives you the performance you're trying to estimate. For a continuous time system, so for time persistent data, you take the integral underneath the curve from 0 to the end of the simulation, where then you take that end of all the way to infinity, and then they average over that, and then that gives you the continuous time estimate. So you're looking for these infinite limits. That's what you're trying to estimate in a simulation that is finite. And so your simulation doesn't run to infinity. You have to stop it somewhere. So counterintuitively, the way we get a better estimate of the long run performance is to actually reduce the amount of data that we're analyzing. We get rid of stuff at the beginning because that stuff at the beginning will be the stuff that usually washes out of those other performance measures. So the question is, how do we choose the warm-up period and the initial conditions to reduce estimator bias while still giving us the desired precision and not force us to run really, really long simulations as a consequence? So yeah, this is a summary of our problem. Early simulations cause the bias, and our two solutions are either just get rid of this stuff or be more intelligent about where we put our initial conditions so that the transient period is naturally shorter. And so that's where I kind of start. And so the idea here is that, like, let's say I set my initial inventory levels not to 0, but to some number. Like, I'm going to assume that I initially have 30 units in the inventory. Or let's say I initially just put customers in a queue. I'm at the bank. I'm going to say, let's just assume that we start with 30 customers in a queue. We're not going to wait for them to arrive at the bank. Or a reliability simulation. Let's just assume some of the machines have already failed. And so that way we're kind of already sort of closer to the normal operating ranges. The question is, how do we choose these? And so one thing you can do is go into the real system and just sort of try to estimate a ballpark. Normally, this bank has 3 people in line. So I'm just going to initialize this queue with 3 people in line if it was like a 24-hour bank. But I might also have mathematical models. And so like in 470, you learn all of these like trivial, simple mathematical models that make all of these like assumptions, and you can solve on the back of an envelope, and generally are unrealistic. But they do have some value. We don't make you take the class for nothing. And that one of the values they can do is they can be used to seed more realistic models. So we can say that in a very, very basic stochastic OR model, you might have a steady state value predicted to be a certain thing based on certain queuing assumptions. And we're then going to start our simulation at that value, assuming that this 470 type model is mostly right. And then we'll let our sim go the rest of the way. So this is a way of combining those two, the mathematical models and the simulation models together. And that's what we call this intelligent initialization. So what you did in Lab 9 was to figure out this warm-up period. And so if you do the intelligent initialization, you hopefully will be able to throw away less time. So you want to kind of do them both. How do I come up with an intelligent initial conditions and then figure out how much data to throw away? And if I've done this step right, then maybe I won't have to throw away this much data. And so how do we choose how much data to throw away? And so you went through a couple of different ways to do that in Lab 9. So for example, here's a trajectory from that, this is the total width trajectory from the manufacturing system you simulated in Lab 9. I just plotted replication 1. And so if you just look at one replication, then you kind of see that, well, maybe it does a rising, and then it kind of reaches a peak, and then it's hard to tell from just one replication, but you might just try and say, well, maybe here, maybe all of this is transient and that's steady state, so I'll cut it off there. But that just doesn't feel very satisfying. So what the book suggests, the other book, the lecture book, is to say, take this data set and run it through a smoothing filter that takes the cumulative average over time. So basically, I take a data set like this one, and I then plot along with it a data set which is basically the average of all points before that point in time. And so over here, I've got this dark line, which is kind of hard to see on this projector, but there's a dark line that has a lot of variance here. And then there is a light line underneath it that has very little variance. And that light line is just the dark line, but you're taking the average over time of every point before it. And that cumulative average has a lot less variance, and it might be easier to see the difference between where things are rising and where things settle out. So that's if you just have one replication worth of data. But in your guys' Lab 9, you had all 5 of these replications to look at. And when you start looking at them all together, you start seeing kind of trends. Like I see this kind of general arc here, and then all of this is noisy, but it looks basically the same. So looking at all 5 of them together gives me the impression that actually maybe this is the transient period. So how do I make this analysis a little more rigorous? Well, what your lecture book suggests you do is to take those 5 replications and for every time point, average them and calculate a mean and a confidence interval. If we do that, we get something that looks like this, where the dark line is the mean and the light lines above it and below it are the 95% confidence interval calculated per each time point. So you've got a moving confidence interval here. And here, it seems very clear to me that there's a transient that kind of finishes off right about here. So maybe this is my warm-up period up to this point here, about time 70 or so. And then everything after time 70 is the actual data I should include, or include in my steady state analysis. And so, so that's all I'm using here is the ensemble average, where the ensemble is just a fancy name for all of the replications pulled together. And so there's my ensemble average, and there's my half-width calculation. Now, I can further smooth that out by running a little moving average on top of that. So just like I did a cumulative average in the first case, I can picture a little boxcar that is moving along the tracks this way, taking the average of the averages within that boxcar. And for every spot the boxcar's in, it's the head of the boxcar is replaced by the average of everything in the boxcar. So the boxcar is moving along, then the average in the boxcar also is going to move up, and that will smooth out this line, and then that will get rid of some of the rest of this noise, so that hopefully I see a much clearer rise and then plateau. And that is a great way to sort of then tell that, okay, that's my transient and that's not. And you should always be conservative. And so if you get a rough idea where the transient is, maybe then go out a little bit, and then just to be safe, because maybe the averaging that you've done has managed to kind of screw up the time scale a little bit. So that's some approaches to come up with that transient, that warm-up period. So most of that sort of came out of Lab 9. Are there questions about this idea of choosing a warm-up period? All right, so there are some caveats, and so if you do choose so initialization bias, if it's been removed completely, then now all that's left is choosing your number of replications to bring your confidence intervals down. And that's great. But if you still have significant bias remaining, some people think, well, I'll just run more replications and that will make my output performance better. But the thing is that if there is bias left over, there's bias in every single replication in the same direction. So regardless of how much replications you run, your confidence intervals will just collapse around a biased estimate of the average. And so you really need to get rid of your bias before you can start cranking up the replications. It can be misleading that your confidence intervals are getting narrower. They may still be biased, even though they're getting very, very narrow. So our simple rule here is that if you have, you want to discard D points, and how do you choose the end of your simulation? Well, what we're sort of suggesting here is that you want the rest of the data left over in your sim to be roughly 10 times the discarded data. Or if in continuous time terms, if your continuous interval is like 5 minutes, then you want to do 50 minutes at least is your end time. And so we just want to wash out any possible leftover bias because there's no other way to get rid of it. Now, we should want to try to make replications as big as possible, up to 25. But the next trick I'll show you is that takes advantage of the fact that if you have 25 replications, your confidence intervals really won't get much, much smaller, even if you increase them much farther than that. There's diminishing returns. And so if I go to 50 replications, I'm not going to get much bang for my buck. So is there another way that I can reduce variance and also manage to take a chip out of these this initialization bias? And that's this trading the replications for longer simulation runs. So the basic idea here is if you go through that analysis and it says, I would like 40 more replications, instead of actually running 40 more replications, take the 25 that you already are running and run them for longer. And so if you already ran 25, do 40 divided by 25, and extend your current simulation time by that factor. So same thing over here. If this is your initialization period and your end time, we're just extending both of them by that same factor. So graphically, this was our sort of pilot study here, where we had our initialization phase and our data phase, and we're growing them both. Now what's going to happen there is that's going to make every replication have a lower variance, which will make the confidence intervals smaller. But it has the other effect that because you've got more data and more discarded data here, so you've got more data washing things out and more transient thrown away, then you have this cool side effect that the initialization bias gets less and less. So once you max out the number of replications, if you really need to tighten your confidence intervals, it's better to run longer replications because then you actually get rid of more initialization bias. And that's a trick you can only do in these steady state simulations. Now going along with that, there's this thing called batch means, which ARENA will try to do for you. And the idea behind a batch mean is that you discard all these data per replication. So if you run a lot of replications, and if it takes, say, 15 seconds just to get to the end of your discarded period, then that means that 100 replications times 15 seconds, you're really cranking through a lot of computational time just to throw away data. So is there a way for me to take a really, really, really long replication and cut it into batches? Can I make these batches sufficiently long so that if I took an average out of a single batch and then looked at the average to the next batch, that these two would not be correlated anymore? Certainly if the batches were of size 1, then the next sample from the replication would be highly correlated to this previous batch. But if this batch is of size 1,000, then maybe the average from these 1,000 numbers would not provide any predictive ability to the average of these 1,000 numbers. If that's the case, then I can run one replication of my sim, discarding only one set of transient data and getting the output from k replications out. So this is a way for me to pay the discarding cost only once and still get all of my replications out. And if you've ever noticed that in ARENA, sometimes if you look at the reports, if the reports has ever shown up for you, it'll say like mean, and then next to it, it might say uncorrelated or something along those lines. Or it'll say correlated next to it under a half width. But if you run it for longer and longer and longer, eventually it shows a half width there. What ARENA is doing is if you only run one replication, it tries to intelligently choose batch sizes for you and then generate variance estimates as if you had run multiple replications. So that even though there's no such thing as a half width for one replication, if you run the replication long enough, ARENA will do this batch means for you. And actually, so that way you only have to discard data once. So that's this idea of batch means. Now, if you want to manually generate these batch means, you have to choose the length of these batches. In the output analyzer, under Analyze, there's something called a correlelogram. So what I've done is I've brought in the data from that width, and I've put it in tiny little batches of an hour each. And I've put it into this correlelogram. And what this correlelogram does is it says, based on the distance away from a batch, how much can I predict the output from the next batch that's that far away? So this is a 1.0 here, which basically means that if I know the data from the current batch, I can predict the data from the current batch with 100% accuracy, 100% correlation from the current time to itself. But as I get farther away from the current time, if I say what happens in this hour, what happens in the next hour, there is some correlation, but it falls off. Once I get down to here, there are points where it actually goes to 0, where this many hours away, I actually don't have any predictive ability. It goes negative. That just means that if I know that the number was positive in this hour, it'll be negative in this hour. And this goes on and on. And so usually what happens to these autocorrelation plots is that they follow an envelope that gets smaller and smaller and smaller. And you can choose a threshold of sufficiently small. And the point at which they enter that threshold ends up being a rough estimate of the minimum size for your batches. You usually make them conservatively a little longer than that. Other statistical programs like MATLAB have even nicer looking correlelograms. So if I bring in the data into MATLAB, here's its correlelogram. and it actually will plot at whatever significance level I want what the thresholds would be. So this kind of shows me that by the time I reach, say, 20, then all of my correlations are within the kind of significance threshold. So basically, I can assume that if I have a batch length of 20, then anything after 20 is not going to be correlated. So what I might do conservatively is to then say, as a good rule of thumb, 10 times the correlation length will end up being the batch length that I want to pick. And so I end up saying that I'm going to choose a batch length of about 200, and that basically means if I take averages over 200 data points, and then I continue to take those averages for the next 200 data points, the next 200 data points, the outputs I get, so this would be like 200 data points, 200 data points, 200 data points, can be assumed to be outputs from independent replications, even though I just got them from one replication. And that's the magic of batch means and tools you can use to pick those. But fortunately, behind the scenes, Arena is doing this, and it will try to generate these batch averages for you. So any questions about batch means? Or any of this stuff about steady-state simulations? Now, next time we're going to be talking about relative. Right now, everything's been about absolute performance measurements. Next time, we're going to actually talk about how do you compare two simulations to each other. But before that, last attendance question for the day. So which of the following is not affected by an increase in your independent simulation replication? So I had 5 replications, and now I have 50. And so my claim is that all but one of these, well, my claim might be that, but I do have this escape hatch here, is that all but one of these will be affected by increasing your number of replications. So is it the 95% confidence interval? Is it the mean estimator variability? Is it the computational time required? Is it the estimator bias? Or are all of them affected when in other words, if I double or if I increase or decrease my number of replications, which one of these does not change? Which one of those is still going to be there regardless of me adding more replications? You guys can think about that between now and Thursday.